Today, we're just going to talk about processes, orchestration, and so on. So for me, myself, I am a very satisfied user of Elixir and Phoenix. I've written some libraries and participating in some events. But this is not why I'm here today. I'm here today to basically talk about a way of writing your programs, especially in today's world. There are certain applications that would benefit from this way of writing programs. And as you may have seen from the topic, the paradigm is basically based on Microsoft Orleans, but in Elixir, or adaptive for using Elixir applications. So 4 things today. First thing, I'll talk about the design rationale, or why shall we use this kind of programming paradigm. Then maybe talk about some pros and cons, talk about special considerations, and then we'll get to the demo as soon as possible. So first, journey to Orleans. Basically, as you all know, if you have written a Phoenix application, you would just create a controller. And in the controller, you have different functions, index, new, and edit, and so on. So these functions are actually more or less stateless. Stateless doesn't mean that it doesn't have state, but rather it means that whatever state created during the lifetime of the function goes away at the end of the function. Maybe it persists in a database, but it's relatively stateless, and it's the default. So your application may look like this, where you have a database and a server, and both things are on the same host. So you can interact with it pretty easily, right? Just curl and you get the information. So your state ultimately goes into the database. And maybe at some point in time, your application has grown and it's grown larger than 1 machine, or maybe you want to have more than 1 machine. So now you have 2 machines, you have a server and a database. And eventually, you get to an even more complicated infrastructure. Now you have a load balancer because you need to have more than 1 server in front of your database. And then you add even more servers. So naturally, when this happens, you can see a certain kind of problem may happen, which is that you have the state in your database, which is on 1 computer, and you have other computers all wanting to access your data. Maybe the database is getting overloaded, so now you're adding even more stuff. So maybe you added a cache server, or maybe you would be like me, so you may have added 4 cache servers, or even an entire cluster of caches. Well, now you have even more problems, because your state is stored on even more computers, and they're all away from where the logic actually is. So basically, this is the idea of Orleans. Basically, instead of moving the data around, where the data is on the database and on the cache, and you want to move the data to your machine, and you operate on data and put it through the customer, you want to move the code around, or to move the data closer. So in any case, the web request may look like this, where you started a request. So if you're familiar with Rails, or maybe you will know, you will write something like before filter, which is like run this function before anything else happens in this controller. So you may say before filter authenticate, so grab the cookie, and in the cookie there's some kind of secret, authenticate the user. And then you load the data, because you cannot authenticate without loading the data. And then you authorize the user, and then you load even more data, and then you operate on stuff, and then you complete your operation, you put the result back to the user, and then everything goes away, and when the second request comes in, when our request comes in, you have to do this all over again. So this can be scalable, yes, for sure, but sometimes your problem is basically so different from this kind of paradigm that a different way of writing programs will be better for you. As you know, this kind of stateless request loop is pretty well understood, because it has been the way we write web applications for decades. Requests come in, response goes out. So the main problem is, as I have explained, the latency is going to be higher, because in any case, you're going to touch your database maybe once, maybe twice, sometimes multiple times. I've seen maybe 1,000 times a page. When you have complicated interactions, or complex interactions, such as I want to put in an order, but when I put in an order, I want to have an event, and the event triggers the notification, et cetera, you start to incur a lot of this traffic inside your cluster. And of course, since every request needs to be authenticated and authorized, sometimes the rules that govern what you can and cannot access as a user is pretty complicated and can go up to like not 5 rules, not 10 rules, but maybe 1,000 rules. And to do this every time somebody wants to do something can cause a pretty severe buildup of overhead. So obviously, Phoenix LiveView has been around for a while. And what LiveView basically allows you to do at the Phoenix level is you collect certain operations that doesn't need to happen a lot of times. And you try to minimize your overhead. So in this case, state is closer to user, and you can essentially amortize the setup cost. I'll give you an example. Let's say I'm a user and I want to fill out a form. The form has like 100 fields, and each field has like 10 values for me to select from. Then if this kind of data structure is entirely persisted in memory, and I can just access it by memory, then I won't have to go to my database, grab all the fields, grab all the possible values, and then do my 100 ORM calls and do so on every single rendition of the page. It would be much faster. Even if you don't benchmark it, it's already much faster. OK, obviously, since you're now keeping more state alive for longer, it requires certain judicious trade-offs. So what is Orleans? Orleans has been discussed numerous times, sometimes at this series of conferences, sometimes at other conferences. But in general, it goes back to this paper, which is pretty old. So when the paper first came out, what the author said was basically, with or without cache, a stateless middle tier is basically less scalable than something else. And that's why they brought out Orleans. So they also introduced something called a virtual actor model. So another thing that caught my interest was essentially their evaluation of Erlang. Basically, they said Erlang still burden developers with distributed system complexities. OK, it's well understood what they have said. And then they started saying the key challenges here are a need to manage the life cycle and to deal with distributed networking and so on. So again, this is very well understood. Anyway, quick overview on Orleans. Basically, within Orleans, the central entity is called a grain. The grain is a virtual actor compared to an actual actor like a gen server or an agent, or basically a process in OTP. So the virtual actor has state. Basically, it's either active in memory or it's persisted in the database, or maybe the grain can be stateless, depending on the design. And according to Orleans, basically you refer to the grains by first refer to the identity. For example, if I'm like a user and I want to access a form, then maybe the grain responsible for my form submission will be keyed against my email plus the ID or some kind of identifier of a form template. So that would be the identity of the grain, essentially a way to find the underlying information. And behavior and state. Obviously, behavior is the logic, and the state is whatever I have, like, for example, the values I put in the form. So this is obviously how the official documentation would illustrate as to how the deployment is like. An Erlang cluster will be deployed like this usually. But obviously, we're here today, and our job is not to look at the source code of Erlang or to read C#. Our job here is to look at what are the things we can take away as Elixir programmers. So if you look at Erlang, basically there are 4 distinct capabilities. First one is obviously to refer to virtual actors by identity. And this is, for example, in Elixir, if you want to send a message to a process, first you have to have the PID or process ID of the process. Otherwise, what you can do is you can query via registry. So let's say if I have a process that's already running, then I can ask the registry, hey, give me a process with this key. And maybe the key is an ID that corresponds to the entity in the database. So there are so many distributed registries inside the ecosystem. There's at least 10 of them that's in active use, maybe even more. In fact, I think every Elixir programmer at some point writes a distributed registry. Second capability is basically automatic placement of grain. And this automatic placement actually means instantiation of a process that serves the need of a certain thing. So essentially, it's choosing which server to run start link, GenServer start link, something like that. So placement in itself is a big topic, and people have already solved this problem. Usually, they will use some kind of consistent hashing. So like libring, for example, provides you with consistent hashing. And Swarm and Horde and so on, they all use this kind of consistent hashing algo to place the processes. But obviously, there are some other frameworks, such as Erlang, which would just say, if your caller wants a grain, and it's not running anywhere in the system, then try and just start a grain on the server, on the host where the request came in. It's basically prefer to place the grain locally. It is also a possibility. Placement is something that is dependent on the application. So you have to do it on a case-by-case basis. The third capability, which is also very important when you have a service, it's automatic deactivation. Because we're now talking about gen servers or agents or maybe state machines, and they stick around, they use memory. So at some point, you need to automatically recover them, basically stop them. But at the same time, if they become needed later on, you have to start them again. So automatic deactivation and activation is actually pretty important, depending on the traffic of your system. Fourth thing is really the persistence of state. And personally, I think this is, again, a case-by-case state. Because sometimes you don't really want all the grains to persist themselves in the same manner by serializing everything and putting it into the database. It can be pretty wasteful or sometimes unnecessary. So it's really best to do this on a case-by-case basis. Right. So let's go forward and just look at what is provided by the Beam. OK. Again, if I were to just take the 4 and rehash it with through the lenses of Beam, then I can get 5 different capabilities. Now we're talking about implementation. So 5 different capabilities. The first one, obviously, is clustering. Essentially, I want a way, so if I have a dynamic cluster, let's say I make a new deployment, and a new deployment brings in 2 new nodes and replaces 2 old nodes, then actually I already have a dynamic cluster. I want to automatically add available nodes to my cluster, so the workload can be spread across all the nodes that are available. On placement, I don't want to end up with a situation where if I have 2 machines, one of them is fully loaded and another one is empty. So I want a good placement algorithm which would evenly spread out the load, and it would be random enough. So with the law of big numbers, the load will be even. The third aspect is registration. And although I say registration, it really also covers the retrieval of registered process information. Essentially, if I have a process running on this server, then when I need a process from something else on another server, I want to be able to find this process immediately. I don't want to go through conflict resolution. I don't want to wait. I want distributed registry. And lastly, recycling, basically stop the process automatically, as we have discussed. So we'll just look at what's available in the ecosystem. So on clustering, basically, right now, it has essentially coalesced around a single library called libcluster inside Elixir. Everything it uses libcluster, essentially. And when a new platform comes out, they write a tutorial, and they tell you how to use libcluster to cluster your application. So it's a pretty well-solved problem. And Erlang distribution itself has improved a lot. And I would say, in most cases, the default Erlang distribution should work for your scale. And because you can tune your system on 2 axes, right? You can add additional servers, or you can make your existing servers bigger. And with these 2 axes used in conjunction, you can achieve pretty good scaling. So I'll give you an example. Say if you were to deploy on Amazon Web Services, then maybe you say, I will use ECS with task networking, and I will tell ECS, register everything I have into a cloud map. Then whenever a new node comes up, it can go to the cloud map, grab the list of every node, and just make connections. And this is essentially how we do it in production, but it's only one of the many ways to do it. Or maybe you have a more traditional network where you just have a bunch of nodes and you can just let them gossip with each other. So every node tells every other node that it is there. There are many strategies available for you to do it. So on placement, again, as I explained earlier, there are many ways to place a process, and this is actually dependent on your problem, and you need to figure out how to place your processes. So consistent hashing is basically how most libraries would do it nowadays. Basically, first, you identify where on the virtual ring every single process would fit, and then you identify which shards of a ring would belong to each of the nodes, and then you can basically use a tree or some other data structure, and then you will be able to work out where each process would fit in terms of which host. So like in this example, 5 hosts, 4 processes. So you can work out the ownership pretty quickly. So if you were to use libring directly, then you can do it like this. Basically, in libring 2 to the 32nd power, that's the number of points on the virtual ring. And one thing that libring did was that it doesn't just use a contiguous chunk for each host, but instead it slices that host into 128 shards and scatters the shards around. And the reason is that if a host were to disappear or when there's some kind of membership change, then the number of workload processes to be relocated is minimized. Yeah. So now we can talk about registration a little bit. Again, the choice of the distributed registry for your application really is up to you. There are more than 10 of them in active use, and every single one of them has defenders and detractors. So try and find one registry that works for you, I guess. Like registration is pretty simple if a registry conforms to the name registration interface. Basically, the registry needs to have registered name on registered name, where its name is sent. And that's basically what you need to make a new registry or a new interface. So the fourth thing is rebalancing. Again, this is somewhat of a controversial topic. And I would argue that it matters more if your cluster is smaller, and it matters less if your cluster is bigger. So essentially, if you have a 2-node cluster, and whenever you make an update, you replace 1 node at a time, then what you would see is that when you replace the first node, everything goes to the second node. Live views may reconnect, and so on. So everything goes on to the second node. And then now you pull down the second node, so everything has to go onto the new first node. And then you replace the second node, and you end up with an unbalanced cluster. So again, there are many ways to balance your workload. Maybe you can do layer selection. Maybe you can do something else. Among other clustering libraries, only Swarm does it automatically with a periodic rebalancing algorithm in it. Again, the other question would be, do you actually need to manually rebalance or bring back any process that died as part of the membership change? It's really up to you. If your system has some kind of constant demand, for example, you're using live view, then as the live view restarts, somehow it would essentially trigger a new process to be located wherever it has to be. Yeah, so relocation may work like this. For example, 5 hosts, now you have 4, and so on. So lastly, on recycling. So essentially a timer on the grain or whatever process to bring it down automatically after a period of inactivity. Again, this is up to your application. Sometimes you don't want to use a fixed timer. Sometimes you want to have a tighter timer, or sometimes you don't want a timer at all. This is actually pretty easily done just by using genState and using some kind of state timeout, or you can do it in any other way. All right. So now we can look at assembling the components into a coherent solution. And as I've shown you earlier, this is a stateless loop of a request. And you can make it stateful. and so on. So I shall show you a few demos. One of them will be using live view, but another one probably will not be using live view. OK. So you will see that if you were to integrate live view, then you will go from this kind of stateless loop to this kind of loop where you will basically have one live view per user, and then they will all connect to some kind of grain or some kind of central process, which is what they want. This is the case of a collaborative editing platform, for example. If you don't have this kind of stuff, then your topology will be different. So with this kind of layout, you can basically also minimize the amount of time spent on security. Or in another case, you can amortize the cost of security checks, because your system may have a kind of use case where most users have very few authentication rules, but some users have a lot of rules. So by separating inside and outside boundaries, you can essentially make sure that most users are not penalized. But again, this is something that's very well understood. Let's get to the demo, I think. So for today's demo, I have prepared several projects, but I shall show you the first one. So I think the game of life is a pretty understood game, isn't it? So it's basically like this, where every cell, every space or square in this case is a cell, and there are specific rules around when the cell becomes alive or when the cell becomes dead. So I've implemented this game of life in a single process. So at the moment, if I were to trigger a re-render, basically reset the entire thing, I can see that for each iteration, it takes about 1,000 microseconds, so 1 to 2,000. I can make this even bigger. So make it whole screen. And the performance is actually pretty good. And I have now prepared another example of game of life. But in this case, I shall use a different way of programming. I will use Erlang, which is the Erlang version of Orleans. And as we wait for compilation, I guess we'll take a look at the code. So in this case, the first thing I've done is essentially I made a grain for the game itself. So the entire game is represented and encapsulated in a single grain. The grain has a state, obviously the ID with height, the timer, and a bunch of cells. And I can say the grain, when placed, should be placed locally. And when it starts, it just starts a timer. And then it would tell all these cells inside the game, which are also modeled as separate grains, to essentially process a tick to progress to the second tick. OK. Next. OK. I will have to use my backup version of the Orleans version of the game of life, because in this case it doesn't want to run. So this is again the version 5, which is without Orleans, and the version 1, which goes backwards, which is with Orleans. As you can see, as I start, I see a lot of stuff printed in the terminal. It's basically every grain being initialized through the Orleans runtime. And I can basically, through the runtime, allow the grains to process the second tick, and each grain would check with its neighbor on the top, bottom, left, or right, what their status is in order to ascertain what their next state should be. It's taking quite a long time, so I guess you get an idea. So obviously, this kind of overhead is a little bit extreme, but in certain cases, it's actually quite good, depending on your use case. I have prepared another think. And I think this one should work properly. It's already running, isn't it? Let's see. Okay, address in use. How to kill the processes. Okay, let's start again. Okay, it seems like it's working properly. Okay, so for this particular demo, actually there is a hosted version, but I will show the demo locally first, and then we'll do the hosted version. Essentially, everybody knows how to play Snake, right? So the Snake game basically works like this. So this is actually Chris's Snake game, but I have made some modifications to the Snake. So what usually is done is that you can do it as a single player game. But I have made the Snake game into an Erlang screen. So multiple live view instances can connect to the same grain, and they can each basically cast votes as to where they want the snake to go. So I think it would be better if I were to make more viewports. Okay, new game. So I can cast a vote of basically up, left, and up in this viewport, and do another one on the right. As you can see, the right, basically there's 0 votes. Now I vote right 4 times, and I can basically vote from every viewport, and the direction with the highest vote will win. So as you can see, the tick is actually quite tight. It's about 250 to 500 milliseconds a tick. So it's not really long enough to show the votes. But you can essentially cluster your applications and do your clustering this way and connect your processes in this manner. I think a better way to do it would be actually to invite everybody to hit the hosted version, see if the hosted version actually works. So if you have a laptop, go to this URI, snake-web.fly.dev, and we shall see if the hosted version is working. Okay, I'm just going to load up the latest game here, and I shall wait here and see if there are players. It seems like there are already players, and they are already playing. I haven't done anything. So I'm going to interfere with them by voting. Okay. All right, let's leave the game there, and let's carry on and look at the code. And we'll just let folks duke it out here. So the thing is, just keep in mind the URI is linked to an ID of the Snake lobby, and going to a root will allow you to get into a different lobby. But you can share this URI as long as the game is not over. So let's just look at the code since time is short. Okay, so what is the architecture of this Snake implementation? It's an umbrella application. It's really nothing special, but I split it into 5 different applications. So the reason why I split it is so it's more modular and better reusable. So first of all, I have this Snake application at the core. The Snake application hosts actually 3 different backends. I have hosted Erlang's, I have hosted Horde, and I have hosted another version of the other process that also goes into Horde. So essentially on Horde, I have both Gen server and Gen state machine versions of the same backend. So in Snake data, I have the database and the handler. In the Snake environment, I have my clustering code, and I have a proxy which serves as a proxy, because usually in my umbrella application, I will have multiple web applications, not just one, and then I have the web application which has the live view. So let's say here is your live view. But actually, first, let's look at the roots and zoom in a little bit. So I have here my roots, where, well, the root of the root is served by the page controller. And I can do a new game, or I can do show existing game. And I would just look at the controller first, page controller. So when I want to render the index, first of all, I go to the database and I find the latest Snake game. So this is not a given. It's not a given that there's a latest Snake game, because while there may always be games, there aren't always going to be games with the right status, which is not over yet. OK, let me check what people are doing. Oh, the game is over. OK. This is an interesting way to die. All right. So in the Snake live, essentially the live view, basically, when I mount, and the live view wants to create a new Snake, then I just create a new Snake and redirect. Otherwise, when I want to show a game, then first of all, determine the kind of backend I want to use. And then ask the backend, what is the current situation? What is the score? And how does the board look like? And what is the status of the game? So the backend will give me this information. And then I will count how many people are on by using Phoenix presence and do my assignments, and off I go. So obviously, depending on the status of the Snake game, I have different renditions, but this is trivial. A new game, obviously, this is trivial. When there's a key press on the page, or when somebody votes using a button, then I do the vote. Otherwise, when the backend tells me, hey, there's a new update to the game, then I basically grab the board and update the board, and live view will do the rest of the rendition for me. When the backend tells me, hey, there's an update on how people were voting, then again, I put in my assignment, and the rendition is handled by live view. And obviously, there's a way to putting a new game. So this is just so. OK, somebody is playing this. And I have interfered with them. I have killed the Snake. But I can click New Game. And when I do this, by using Phoenix pops up, the entire universe of games tied to this particular ID is refreshed. So that's why you see there's a handle info, because this comes from pops up. OK, and obviously, this is Phoenix presence. So this is basically how the live view looks like. And as to the template, it's really pretty simple. First of all, I have a bunch of voting buttons. And then I have a board. And then I render the obstacles. And I render the cherries. And I render the Snake. And all of them are little divs. So it's pretty straightforward. It's HTML. Let's look at the backend, because I think this is the interesting part. So again, I said I've written 3 versions of backends. So let me show you the first version using Erlang. The backend has some kind of state. The state has a game, has a timer, status, the score, heading, vote, and board. So when I create a green, I say I want to prefer local placement of the green. Because as I discussed earlier, in Erlang, you can tell Erlang, I want to place the green locally. So if it's not running in the cluster and I want it, then put it on my host. So that's prefer local, or you can say random, or you can use another strategy. And I can tell Erlang, when you want to activate the green and you want to produce a runtime state, then get a game from the repo, and then get the board from the snapshot. So the key here is that just by using Erlang doesn't mean that you're entirely stateless. You can still persist your state periodically to the database. I'll explain this later if there's time. So obviously, if anybody calls and wants to load the state, and I just give them the state, and when somebody calls in and say, I want to vote for this heading, then I update the vote, and then I carry on, maybe start the timer, maybe not. And when the timer is done, when the state is halted, meaning the game is over, then I cancel it. Otherwise, I advance the board by 1 tick, and then I save the game immediately. So this pattern is basically checkpointing. And the flexibility here is you can determine where your checkpoints may be. So let's say if you were to do a collaborative editing platform, and you have a bunch of people, slinging CRDTs around, and they're editing the document, maybe it's actually bad performance to save every keystroke. But you can do some kind of checkpoint where every 5 minutes, save the document as is, and and you may have some kind of write-ahead log somewhere running on parallel to it. So you can do this kind of checkpointing, and it's pretty good. So we use it a lot in other places, such as forms and so on. We just take a snapshot periodically. So we have reasonably robust persistence. Okay, and obviously Evadne board. Since this is not a CS course, I will skip how the snake game actually is written. Just I can tell the board, hey, here's the board, and here's a new heading, advance and tell me what's going on. So maybe the snake is growing longer, maybe nothing happens, maybe the board is entirely full, or maybe the snake hits something. So with each of the 4 outcomes, I do the right thing. So this is how the backend works if it's using Erlings. Now, if you were to use Horde, then it's an entirely different matter, because Horde acts very different from Erlings in terms of how you should interact with it. So let's say if you were to do it in a Gen server, obviously you have state, and you can initialize the game, initialize and get a state, and then when you load, you do the same thing, vote, you do the same thing. It's substantially the same, but using Gen server. So this is where I shall highlight how the interaction with Horde is done. So with the Horde library, basically, I have some clustering magic. Whenever a new node comes in, I tell Horde, hey, track this new node. So my tracker tells every Horde cluster on the node, hey, here's a new node, please add it to your memberships list. And so it works automatically. Anyway, so when my Gen server starts, obviously I have some startling stuff. When Gen server starts, it always uses via naming. So Gen server registers with Horde registry, and here's my actual module and actual key, and so on. And here is how a new process essentially is placed. So from line 70 to line 95, essentially, it's find an existing process or place one for me. Essentially, this is how you do it with Horde. So obviously, lookup or start. And Horde has a CRDT inside of each distributed registry. And it handles synchronization of memberships automatically for me. So again, lookup or start. And by lookup, it's Horde registry lookup, hey, where's my process with this key? And maybe I get an answer I like, or maybe it's an answer I don't like. Maybe there's none, or maybe there's too many. So yeah, that's how you do it with game server, with Gen server, including this Horde add-on. So another thing that the Gen server doesn't do by Erlings, and this Gen state machine version would also do, is the ability to stop the process after a certain amount of time, essentially recycling. So recycling is done pretty easily by way of Gen state amming OTP, or by Gen state machine, which is the Elixir wrapper that allows you to address it with Elixir. You don't have to use it. Because when I start the process, I tell Gen state machine, hey, start a process, and here's my name. And the name obviously contains the game ID. When I initialize a process, it's basically the same thing, but I will always pass in something. I'm passing an action, a timeout action. So essentially, I tell Gen state machine, here's a state timeout of 45 minutes times 60 seconds a minute times 1,000 milliseconds per second. This is a state timeout. If nothing happens for this long after entering the state, then tell me about it. So I put in this timeout action. And obviously, when I get a call, I say, OK, this is your reply. Here's a timeout action. And when I get a call, again, maybe I update the data. And here's a timeout action again. So the thing here is that whenever you enter a state again before the timeout hits, the old timeout goes away. So let's say if you have a timeout of even, like, let's say 60 seconds, but your game updates 1 time per second, then essentially your game would not time out until it's done, until the timer goes away. Because every 1 second, you might re-enter the same state via Gen state M, and so it invalidates the timeout. So it's pretty nifty. OK, so let's see what people are doing. This is very impressive. I don't know who was doing it, but they've got 42 points, and I shall leave it. OK. So I guess there might be some time for questions. Is there any question on Hoover? Let's see.
There are currently no questions in Hoover.
OK. Well,
do we have any questions in the audience? We have 2 minutes. Oh, please come and fetch the ice cream.
Yeah.
Also known as the mic. So eat it like an ice cream, like this. Yes.
So, OK.
So it's hello, Mike?
Yes, lovely.
OK, good. So have you ever encountered the need to set your processes to hibernate to conserve some memory?
I have not particularly tested that.
To actually, trigger the process level garbage collection.
No, for my use case, I never had to do that, but it doesn't mean that you shouldn't.
Okay.
I haven't done any benchmarking related to that because, in my opinion, if I don't need it, I just stop it.
Yeah, I had to do that, and it was causing some difficulties with the registry. So some timing issues. I just was wondering if you have encountered that. Thank you.
Just made a screenshot of that. OK, so on the registry synchronization and timing issues, yes, I did find that sometimes it happens, especially when let's say I have 2 hosts and I have a load balancer, which is round robin, and I hit both load balancers very quickly by asking for the same grain from different machines, then sometimes I hit a timing issue. I look into several solutions, and really there isn't a very good solution, but I'm considering using something called advisory locks in Postgres, essentially some kind of lock that's very granular, which will allow me to essentially kill the second illegitimate grain if needed, and if it's unfortunately placed in such a way that's not consistent. Do we have any further questions?
Then I think we will give it up. Thank you.
Thank you.